Welcome to tutorial on constraint modeling for planning. My name is Barták and I'm from Charles University in Prague, and I'm working in the area of constraint programming for almost 20 years now, and I try to do also some constraint models for planning. So first, let me try to answer some questions that you may be typically asking when deciding which tutorial you would like to attend. So first, what's the topic of this tutorial? Well, the title says it. It's about how we can apply constraint satisfaction techniques to solving planning problems. In particular, I'll be speaking about how we will model planning problem as a CSP. So now the question is, what is a CSP? What is a constraint satisfaction? It's a technology which is very similar to Boolean satisfiability. I would say the major difference is that we have a larger range of constraints that we can use. So it's a technology for solving combinatorial optimization problems, and I mean combinatorial meaning discrete problems. So why we should look at CSP? First, it's quite powerful technology. It's in some sense it's not that complicated to be used if you understand a bit how is it working inside. And also from the perspective of planning and scheduling, the nice property is that CSP can be used as a bridge between planning and scheduling, because it's used quite frequently in scheduling for resource and temporal reasoning. So as soon as we are adding these constraints to planning, CSP can be a good technique there. In this tutorial, I will start with describing how CSP is working. About 1/3 of the tutorial will be dedicated to it. You may be asking why I should understand how CSP is working if I can use any constraint solver. So the reason is that if you understand how the technology behind the solver is working, then you can exploit it better. And in some sense, it means that you can exploit it at all, because sometimes the behavior is not intuitive, and if you understand what's happening behind the scenes, you will understand why your constraint model is working as it's working. So these are just few questions that I try to answer right now. Of course, if you have any questions during the tutorial, just interrupt me and ask the questions, and I will try to clarify it. So the outline of the tutorial, I already mentioned it. In the first part, I will very briefly try to describe how CSP is working. It will be just about the mainstream CSP techniques, which is basically a combination of consistency and search. So let me ask the question, who is familiar with CSP, constraint satisfaction techniques? Almost everyone. Okay, so I will try to be very fast in this part, so it's not boring, and we can go to the second part, which will be about how we can model planning problems as CSPs. When talking about planning problems, I will focus on classical planning problems where we have non-derivative actions with preconditions at the beginning and effects at the end. And I will show a couple of models for sequential planning where we are looking for a sequence of actions, and then I will show how we can modify these models for parallel planning where we allow parallel actions at any step. Okay, so let me start with CSP, and the best way to introduce the technology is using examples that everyone knows. And I think that for CSP, the best example to demonstrate the technology is Sudoku. Right? So I guess you know Sudoku. It's a combinatorial puzzle where we have a grid of 9 times 9 cells, and we are looking for digits to be filled in this grid in such a way that each row is a permutation of digits 1 to 9, or in other words, there are no two cells filled by the same digit. The same for the same column, and also for the subgrid like this one. What makes the problem complicated is that some cells are already pre-filled by some numbers. Otherwise, the problem would be quite simple. So this is a solution, and how we can find a solution if we are solving CSP manually. It's by exploiting the information that we have about the properties of the solution. And these properties are, we can call them constraints, which are saying that the numbers in a single row should be different, right? So we can use this information to solve Sudoku. So if we have this part of the Sudoku, like this one, and if you look at number 1, you can see that already number 1 is here, so it can't be in any cell in the first row. And specifically, it can't be in these two positions. And the same can be said for the number 1 in the second row. So we can say that it's not possible 1 to be there. So if you look at it, the only remaining position for 1 is this one, right? So we do this reasoning when we are solving Sudokus. And if we see Sudoku from a more general perspective, we can say that each cell is a variable. And there are 9 possible values that can be assigned to this variable. And the properties of Sudoku describe constraints, like the variables corresponding to variables in the same row should be different, and the same for the column and for the subgrid, right? So it's like a binary inequality constraint, or we can see it as an all different constraint between all variables in a single row. And what these variables are doing is for us is that they are, what these constraints are doing for us is that they are pruning values violating the constraint. So if you look for the first row, 5, 3, 7 is there, so we can remove these values from the domain of that variable, and we can do the same with the column. So this is basically how we are solving Sudoku, by removing infeasible alternatives, and this is basically what is a CSP. So Sudoku is a specific example of a CSP. Formally, constraint satisfaction problem is a triple where we have a finite set of discrete variables. They usually describe some properties, some attributes of the solution that we are looking for. Then we have domains, which are slightly different notion from the domain in planning. So domain is a set of values for a given variable. It could be the applicable actions in planning. Sometimes there is just a single global domain, and the specific domains for each variable are defined by unary constraints, but this is just a technical issue. And finally, we have the constraints, a finite set of constraints, and constraint is any relation. That's what makes it different from Boolean satisfiability, where constraints are clauses. So we can use any relation in CSP, like action A is different from action B, set of variables should be different, or so on. These constraints can be expressed in extensional way, and this is how we will be using the constraints frequently in planning, meaning we describe the constraint as a relation, which is basically a set of tuples of values satisfying the constraint or violating the constraint. The other way is also possible. Or we can describe the constraint using a formula. I mean, logical formula, arithmetic formula, and we can also use what's called a global constraint, some specific type of constraint like the all different constraint. Okay, so what's a solution to a CSP? A feasible solution to a CSP is an instantiation of variables that is complete and consistent, which means that each variable has assigned a value and no constraint is violated by this instantiation. Okay, sometimes we are looking for all feasible solutions, or we may look for just one solution, or we may need to select some solutions. Sometimes to define which solutions we would like to select, we can define optimality. So we use an objective function that is defined over the set of variables and orders all the solutions, and we are minimizing or maximizing value of this objective solution, right? So it's a function that maps feasible solutions to real numbers. So this is about CSP, how we are solving CSP. So let me show another example. Before going to this example, when we want to use a CSP in practice, basically we are doing two tasks. The first task is what's called a problem modeling. This is a description of a CSP of a problem as a CSP. So we have real life problem, and we would like to formalize the problem somehow. This is what we will be talking about in the second part of the tutorial. I'll be showing models for planning problems. And of course, then we need to solve the models, which is the process of assigning values to the variable satisfying all the constraints. In this tutorial, I'll be going in the reverse order. So we will start with the solving techniques, and then I will show you how we can model some problems. So I promised another example that shows how we can solve CSPs. And this is another popular example used to demonstrate the technology, and this is n-queens problem. So I guess you all know n-queens problem. The task is we have a chessboard of size n times n. We have n queens, and you would like to place these queens to the chessboard in such a way that no two queens are in conflict, which means that no two queens should be in the same row, single column, or single diagonal. So how we can model this problem? There are many ways how we can model it. The usual modeling decision for n-queens problem is that we assign each queen to a specific column, and we are just looking for a row of the queen. Another model is that we are looking for both row and column of the queen, which is a larger model, less useful. So it means that we will have n variables, and each variable will indicate the row of the queen. So the domain will be the number, the index of the row. What will be the constraints? Well, no two queens should attack each other. So we can express these constraints using formulas. Like if I take two different queens, I and j, then the rows assigned to these queens should be different. Or and if I take two queens, then this constraint is basically describing that these two queens are not at the same diagonal. Because if they are in the same diagonal, then the vertical the distance between the queens is the same as the horizontal one, or I don't know which one is this. So they should be different. I mean, the distance between the columns of the queens should be different from the distance between the rows of the queens, because otherwise they are diagonals. And to describe both diagonals, we can use the absolute values here. Okay. So how we are solving the problem? So basically, the technology is based on a combination of search and pruning infeasible values. So we can start with the first queen, and we can allocate the first queen to its position, and we can use these constraints to prune infeasible values from domains of all other queens, right? So for the second queen, values 1 and 2 are removed because they are inconsistent with this queen. Now everything seems easy, so we can continue with the second queen, we can place it here, and we can repeat the process. We can remove infeasible values from future variables, and now we see that what happens is that for the third queen, there is no value remaining. So we know there is no solution when the first two queens are allocated like this one. So we can backtrack in the search, and we can move the second queen to a different position. So we know this position is forbidden, so we move the second queen to that one. Well, again, we remove the values. It still looks like it's consistent, but if we place this queen, immediately we see that the fourth queen is not possible to be placed there. So we backtrack. There was no other alternative for the third queen, for the second queen. So we need to backtrack till the level 1. We place the queen here, and again we repeat the process. We remove infeasibilities, and we can find a solution. So this is a process which is called a forward checking. So we check the constraints ahead, but not completely. We can do it even better. So more formally, when we are solving CSPs, and the constraint solving method is based on combination of search, which is sometimes called labeling, because we are labeling the variables, we are instantiating the variables one by one, meaning that the variables are somehow ordered, and we are selecting the values from the domains in some specific order. I will mention some heuristics for these orders in a minute. And then after each instantiation of each variable, we verify the constraints. And by verifying, I mean that we can also prune values from domains of future variables. Okay. This is called MEC, maintaining R consistency, or a look-ahead technique, and the algorithm is very simple. It looks like this. So we have a set of variables, domains, and constraints. If all the variables are instantiated, then we are done. Otherwise, we select some not yet instantiated variable, and we try all values for that variable, meaning we assign the value to the variable. We run some consistency procedure. I'll be talking about them in a minute. If everything is consistent, I mean the test is okay, then we continue with the labeling of the remaining variables, and you can see that the domains of the variables can be pruned by the labeling procedure. And if we return some solution, which is not a failure, we have a solution. Otherwise, we just try another value. And if we try all the values, then we return a failure, which means we should backtrack to the previous level. So speaking about the heuristics for selecting the variables and values for them, the most typical one for selecting the variables is called fail first principle, meaning select the variable whose instantiation will probably fail. And there are some instances of this heuristic, like the DOM heuristic, which says select the variable with the smallest domain first, or select the variable with the largest number of constraints in which the variable is participating, which is called the DEC, degree heuristic. Sometimes a combination of these heuristics is used, DOM plus DEC, and there are other constraints. So what's important? Other heuristics. So what's important is to understand that for the instantiation, we should select first the variable which is somehow critical, which may lead to failure, because if there is a failure when assigning value to this variable, we should discover it early during the search. Okay, and it defines the shape of the search tree that we will be exploring. About the order of values, of course, we should select the value which belongs to the solution, which is called a succeed first principle. Of course, it's hard to deduce which value is it, because if we know which value belongs to the solution, we don't need to do any search. We can find the value immediately. But there are some tricks, like values that are supported by other values in other variables are good candidates. Frequently, this heuristic is problem dependent. So we know our problem, we know what are the typical values for the variables, so we will use them. And I will show you some of these problem dependent heuristics for planning that we developed. Okay, so this defines the order in which we explore the search tree. Okay, so this is about search, but actually what's more typical for constraint satisfaction is inclusion of the consistency techniques. So very briefly, if we have a problem like this one, two variables A and B, A is smaller than B, then we don't need to blindly explore combinations of values and verify whether the constraint is satisfied. If we know the semantic of the constraint, we can look at the constraint and we can immediately say that if A should be smaller than B and the maximum value of B is 5, then obviously the maximum value of A, which could be consistent with any value of B, is 4. So everything which is 5, 3, and 6, 7 is not possible for the value A. And similarly for B, because B should be greater than A, minimum value of A is 3, so the minimum value of B, which is consistent with 3, is 4. So 1, 2, 3 can be removed from the domain of the variable B. So we can use the constraint actively to remove values which are violating the constraint according to current domains, right? So this is what I just described. So we have this constraint and we can propagate information from one variable to the other variable through the constraint, right? So we can propagate the information from B to A. So we remove all values inconsistent in A, and we can of course go in the other direction to reach the largest level of consistency. So this is basically called arc consistency, and it's called arc consistency because we have an arc between the variables that we are using to connect the variables. And this is a definition of arc consistency for binary constraints. So if I have a constraint between variables vi and vj, then I say that this constraint is arc consistent in the direction of ij if for any value of x in the domain of the first variable there exists a value in the domain of the other variable such that the pair satisfies the binary constraint between these two variables. And of course this is just a one direction, so if I want to make the constraint consistent, I should make it consistent in both directions. Okay? So we say that the CSP is arc consistent if every arc is consistent. So this is a local consistency technique because we are looking for each constraint separately, and we make each constraint consistent separately. So how we make a single constraint consistent in general? Because I said constraint is any relation. So how we can ensure that the constraint is arc consistent in general? Well, we can follow basically the definition. So we will explore the values of the first variable, and for each value we try to find a support, a value consistent with it in the other variable. And if there is no support, we can remove the value from the domain of the first variable. Right? So this is for a single constraint. This is how the algorithm looks. Very simple. Explore all values in the first domain. Try to find a value y in the second domain such that it's consistent. If it's not there, then simply delete the value from the domain and remember that you deleted something. And you repeat the procedure for each value. So the time complexity of this procedure is d square if d is the size of the domains approximately. We can do it slightly better, but in general we need to do something like this. So this is our consistency for a single constraint. What about making the whole CSP consistent? So we need to make all constraints consistent. So how we can do it? Let's make the problem more complicated. Now we have two constraints there. So we start with the initial domain store, which are the domains 1 to 6. We select one constraint and we make it consistent. For example, x is smaller than y. So we removed all of the values from the domains of x and y which are violating the constraint. So now we have a store where the domain of x is slightly small and the domain of y is slightly smaller, and this constraint is now consistent. So now we go to the other constraint, z is smaller than x minus 2, and we made this constraint consistent, which changes the domains of variables z and x, as you can see. So z is now 1, 2, because the maximum value of x is 5, minus 2 is 3, and z should be smaller than 3, so only 1, 2 is satisfying. And similarly, we propagate the information from z to x, okay? But, so now the constraint z is smaller than x minus 2 is consistent, but if you look at it, the constraint x is smaller than y is no more consistent because we changed the domain of the variable x. So we need to check this constraint again, the consistency of this constraint. So, and we can see that actually the domain of the variable y has been really reduced. And now this problem with this set of domains is arc consistent. You can verify that each of these constraints satisfies the property of arc consistency. So a simple procedure how to achieve this consistency is repeating calls of the revised procedure for each constraint until any domain is changing. Okay, so this is called AC1. It's not very efficient. The most widely used procedure for making the problem consistent is called AC3, and it's motivated by observations that if I change the domain of variable z, I don't need to re-verify consistency of constraint x is more than y because no domain of x and y has been changed. So it's not necessary to change to verify this consistency. So basically, if we change domain of some variable, then all constraints that are using this variable should be verified. Meaning we should propagate this new domain of this variable to these variables connected to that constraint. With one exception. The domain of this variable has been changed by some constraint, okay? So we don't need to revise the constraint in the opposite direction, the reverse direction, because it will not prune the domain of that variable, right? So no value here lost as support in this variable, so we don't need to verify this constraint. So this is how the procedure looks. We have a queue of variables, a queue of constraints, pairs I and j. So we are repeating the procedure until the queue is empty. We select the constraint, we revise the constraint, we make the constraints in a given direction consistent by deleting some values in the domain of variable k. If the revised procedure returns true, it means that some value has been deleted. So we put all the constraints, all the arcs directed towards the variable k back to the queue. Okay, and we repeat this process until either any domain becomes empty, then the problem is infeasible, or the queue becomes empty, then the problem is arc consistent. Okay, so this was about the mainstream techniques for question. Yes. Yeah, so the major difference from AC1 is that in AC1, we make all the constraints in the queue consistent. If anyone returns true in the revised procedure, then we make all the constraints again consistent, right? So in each iteration, we verify all the constraints. In this case, we start with all the constraints, but we placed back to the queue only the constraints affected by the change of the domain. So it's a much less consistency check because we are not checking constraints like this one if z is changed. Okay? So that's the major difference. Other questions? Yeah. Year? Oh, last century. I think it was already in 70-something in one of these first constraint networks papers by Alan Maxworth. So I don't know, 75, I don't remember 77. So it's a very, very old one, but still it has, in some sense, the best ratio between I mean, this is not optimal. We can find a better algorithm to make the problem R consistent, but this one is working very well in practice. It has a good practical properties. It's not optimal algorithm, there is an optimal algorithm, but it has worse properties in practice. So that's why this one is used. Any more questions? Okay. So let me very briefly summarize what's the difference between CSP and enumeration. Because if you are talking to people outside CP community about constraint programming, they say, oh, you mean these simple enumeration techniques. Well, yes, we use search in constraint programming, depth-first search. But if we solve the n-queens problems, this is what I would call enumeration. So we really enumerate all possible combinations of values using backtracking, and we verify the constraint, and the constraint is violated, we stop, right? So this is a search tree for solving 4 queens problems. So we need 19 attempts to find a solution, and we really need some strong heuristics to guide the search if you want to use a pure backtracking without anything else. If we introduce just the forward checking that I showed you at the beginning as an example of how we can solve constraints, we just need 3 attempts. And forward checking means that we just verify the constraints in some way in one direction, right? So we assign the value and we propagate it in one direction. And we can do it even better, because if we make the problem arc consistent, as I showed you later, we can solve the problem even faster. We just need 2 attempts at the level of search procedure to find a solution. Of course, each step here is slightly more complicated than in backtracking, because we are running the AC3 procedure there, right? So this is an example that I'm always using to show a difference between simple enumeration and constraint programming. So it's really about the consistency, what makes constraint programming different from enumeration. Okay, so let's now go to modeling problems. So when we want to solve real-life problem using constraint satisfaction techniques, we need to model the problem, which means we need to express the problem as a CSP, and then we can use these generic CSP techniques to solve it. So we need to do decisions like, what will be the variables that will be used in describing the problem. So the variables, of course, need to denote the solution that we are looking for, and they also define the search space, because then we will be labeling the search variables. So for example, in n-queens problem, you can say that the variable is a position of a queen, which means we have 2 coordinates. But then you have a domain n square for each variable, right? And we have many symmetries there. So if we decide to model the problem by assigning the queens to columns, for example, then we have just the domains of the size n, much smaller search space, and many symmetries are removed because we are not swapping the queens between the columns. Of course, we can use the model where the queens are in the rows. We can combine these models. There are many ways how to do it, but it's very important to decide what will be the variables. And there are usually many ways how we can do it. We can sometimes even swap the role of variable and value, right? So in n-queens problem, we can use a variable for each square, and we can ask, is a queen there or not, a Boolean variable. So we swap the role of variable and value. It's possible, and it's very important in modeling. Okay, and then of course, usually by deciding what will be the decision variables, we already know what will be the domain of these variables. But again, we may formulate the domains in slightly different ways, and it will influence how we can describe the constraints. Like you can map the domain to natural numbers, and if you start with 0, you may obtain a slightly different constraint than if you start somewhere else. And finally, we need to formalize the constraints. Frequently, we will be using existing constraint solvers. So we will not be encoding the algorithms behind CSP. So the definition of constraints that we can use will be given by which constraints are available in that solver. So you can't use any constraints. You just need to use constraints that the solver provides to you. Sometimes it might be necessary to introduce some auxiliary variables, so you can express the constraint at all, or you can make the constraints much simple for expressions. So basically, I don't know, perhaps you can't read this picture, but modeling is this part here where it's written, this is where miracle happens, right? So we have a problem, we have a CSP, and we need to bridge it. And this is where we need some experience in modeling. There are some rules of thumbs how we can do it, but it's not like a textbook which tells you this is how you should model the problem. There are some rules, but it's not really deterministic process. There are options that you need to explore, and you need to know something about solving some constraints. So now I will show you how we can model planning problems as CSPs. And as I said, I'll be dealing only with classical AI planning techniques. We can extend these models to more general planning, like a temporal planning, but for simplicity reasons, I will just present the models for classical AI planning, which means we are looking for usually shortest sequence of actions called a plan that transfer the world from some initial given state to a final state described by some goal condition. Okay, so the major difference from, let's say, classical PDDL models will be that I will be designing the models for multi-valued variables. So rather than predicates which are true or false in a given state, I'll be using variables like location of the robot, and the values of the variable will define the particular location, and values of all these variables will define the state of the world. Okay, and action will be described by preconditions, which will be constraints over the state variables, and we'll assume that these constraints will be always in the form variable equals some value. Robot is at location 1, and the effect will be assigning of values after making the action, after applying the action to a given state. So it will be a description of how we change the value of certain state variables. And I'm talking about grounded actions, not about operators. So this is an example that I will be using when I will be showing some specific examples of constraints. So a very simple problem. We have one robot, 2 locations, and we have one container, and the container can be at 2 locations, or it can be loaded to the robot. So to describe a state of the world, we use 2 state variables: location of robot with values location 1, location 2, and position of container, which could be location 1, location 2, or robot. And these are all, how many? 6 actions, grounded actions that we can use, moving the robot from one location to another location. So precondition is the robot is at location 1, and the effect is it will be at location 2. Moving the other way, loading and unloading operations. Loading and unloading is where the interaction between the robot and the container is happening. So for loading the container, we need the position of robot, and location will be the same, and then the position of container will be changed to be on the robot. And unloading means that the container will be placed to a given location. So that's just a very simple example to demonstrate some of the constraints. So if we want now to model a planning problem as a CSP, there is one critical problem, and the problem is that in planning we don't know in advance how many actions will be in the plan. But in CSP we need to define all the variables in advance, all the domains, all the constraints, right? So that's a problem, because we don't know how many actions are there, so we don't know how many variables we need for the actions. So we will use this classical approach of finding the plan by iterative extension of the length of the plan. So we will be encoding the problem of finding a plan of a given length as a CSP, and if we fail, if there is no plan, we extend the length, right? So this has been introduced for SAT-based planning, and the same approach can be used for CSP-based planning. So the idea is that we will be modeling the problem using 2 types of variables: state variables and action variables. So we will have a state variable describing the values of the state variables in a given state. For the initial state, we know the values, so it's easy; they are instantiated. Then we will have action variable which will be really variable that we are looking for which value we are looking for. And then we will have again state variables describing how the state will look after we apply this not yet known action, right? So if you want to model the problem with n actions, then we basically introduce n+1 state layers. Each one is described by a set of state variables and n action variables here. So these are the variables. The domains are quite clear. So for the state variables, these are the possible values of the state variable. For the action variables, these are the variables describing some indexes of actions, right? And yeah, for the go state, we assume that the go state is specified by values of certain state variables. It could be a constraint. There is no problem. But for simplicity, we know the values of certain variables there. And we need to describe constraints that are connecting these variables. And these constraints will be describing state transitions. So in the simplest way, what we can do is that we connect the variable with some variables in the preceding level to describe the precondition. Similarly, we can connect the variable with the state variables in the next layer to describe the effect. And that's not enough. Do you know what's missing? Classical problem from AI. Yeah, exactly. Which is called a frame problem. So everything which is not changed by the action should remain the same. So we need also to introduce a frame constraints that are saying these variables are not changed. Okay. So that's the basic idea of a straightforward model. And then how we can do the search procedure. So it's better to use backward search because we can follow the fail first principle. And the number of actions that are relevant to the goal is usually smaller than the number of actions applicable to the initial state. So based on the fail first principle, it's better to start instantiation of variables in the backward direction. Okay? And the important thing is that it's enough to instantiate just the action variables. Meaning in the labeling procedure, we don't need to include the state variables because the state variables will be instantiated by means of arc consistency automatically. So we don't need to assign values actively. It will be done behind the scenes by the constraint, right? And as I said, we'll be trying only actions which are relevant to the goal, which means this will be a small number of actions for the last action variable than for the first action variable, which is the reason behind backward search. Okay, so let me now be more specific about how the constraints should look. So this is a model that I call a straightforward model. You can find it in the famous automated planning textbook by Gallup now and Traverso. So they describe the formulation in a very straightforward way. So they say, okay, if I want to describe the action, I can say that if the action variable equals a given action, this is a constant, then implication, some constraint must be true between the state variables in the previous layer. Okay? And if I want to describe the effect, it's the same. If a given action variable equals a given action, then some effect constraints must be true in the next layer. What does it mean exactly? So if we have this robot moving problem, so we can say if action variable is moved to 1, move from location 2 to location 1, then the precondition is that the location of the robot at the previous layer equals location 2. So this is a variable. This is a constant, okay? And regarding the effect, it's very similar. We just say that the location of the variable in the next layer will be location 1, okay? So it's a set of implications. And recall that constraint can be any relation, right? So this is a description of relation in a logical way. So these are action constraints, and regarding the frame constraints, we can say that for each variable, if we have an action which is not affecting the variable, not changing, not touching that variable, then that variable will be same after applying the constraint as it was before applying the constraint, right? So that's it, right? So we can describe the problem with a lot of these implication constraints, but there's a problem. Yeah, this is how it may look, okay? So there's a problem. And the major problem is that implication is just a syntactic sugar for disjunction. And disjunctive constraints in most constraint solvers are propagated in a very weak way. It means that if you have a disjunction, you can write a constraint as a disjunction, but usually not full arc consistency is implemented for this disjunction. It's a form of lazy consistency, meaning the system verifies if any part of the disjunct can still be true, and if this is the case, then the system is happy with it. No pruning of the variables, because we don't. If there are more of them, more parts of the disjunction can be true. Then you need to do some more complex pruning, right? So the disjunctive constraint is basically waiting until all but one disjunct are proved to be violated, and then you use the remaining part of the disjunction as a classical constraint, and you propagate through it. So it's lazy, right? It's waiting until the last moment, and then you propagate. So it's a problem, because at the end, all constraints in this model are disjunctive constraints. So all solving must be done at the level of search, because the propagation will not help you. And moreover, there is a huge number. So it does not propagate via the constraint. There's a huge number of these constraints. And by huge, I mean just, this is for each action. Right? This is for each state variable. So just assume that you grounded the problem with 10 robots, 10 locations, then immediately you have 1,000 move actions. Just move actions. And then you need load and unload and so on. So really huge number of constraints, right? So the propagation loop, the AC3 procedure, will be trying all constraints to propagate, right? So it will take a long time to verify each constraint without any effect, because no constraint at the end will be propagated. The system will be just trying to propagate. Okay, so we say no, this is not the way how we can model it properly. It's straightforward, it's easy, but it's really not working. So we proposed an extension. We say, okay, can we model the constraints in a more efficient way so we can exploit the pruning? And the answer was yes. But rather than using logical constraints, let's use an extensionally defined constraint. This is called the table constraint. It means that we basically describe the constraint as a set of tuples satisfying the constraint. And the idea was very simple. We just need to be careful about the size of the table. So the idea was very simple. We took just the action constraints, and we defined a table which somehow described the state transition, but not in a complete way. So in this table, we just describe the preconditions and effects, but not the frame constraints. So the size of the table will be the number of constraints, will be the number of rows in this table, and the number of columns will be, one column will be for the action variable, and then we will have columns for all state variables in one layer and all state variables in the next layer. Okay, and each action will be described by one row where we specify just the values of the variables in the precondition, and we say that any value can be used for variable which is not part of the precondition. And in this case, we make the table much smaller than if we really describe all combinations of all values. And similarly for the effect, we really describe just the value that is changed by the constraint. And for this value, we say any value can be there, right? So this is a description of relation between state variables in one layer, action variable, and state variables in the next layer. It's a constraint, okay? Of course, we want to say that these two variables should be the same. So for this, we keep the original frame constraint expressed in the implication that do the propagation for us. So if we select the action, this constraint will verify the precondition and effect of the action, and then this constraint will put these two variables equal. Right? Question? Yes. You mean we don't need to assume load 1 in the frame constraint? No?
No, I'm saying your value in rlog s is load 1, and rlog s plus 1 is load 1.
Okay.
So could you not omit those two?
Well,
Or is it
the reason why these two values are there is that they are part of precondition and effect description, right? So for the move action, we say that the precondition, for the load action, load 1 means loading at location 1, we say that the robot and container must both be at location 1. Right, so both must be location 1, and this is what we say at the end. Well, perhaps this is not correct. I think we are not changing. So I think by loading we are changing just the position. But if we just encode it, well, we can put it there. I mean, it's not wrong, but according to what I said, the semantics, I think this should be empty, and the value should be moved by the frame constraints there. Probably, I think. Yeah, the first lock must be there, but because it's in precondition, but this is not a real effect. So I think this should be an empty cell here, according to my semantics. It's not wrong, but it should be empty. Okay, so that's the reformulation. I will show you in a minute what's the effect on efficiency by changing the logical constraints to table constraints. So now let me show another model. I will compare all the models at the end. So this is a model proposed by Mingdo and Rokampambati. It's based on the idea of graph plan. So they call it GP-CSP. And they say, okay, what if for each state variable we define which action is setting the value of this state variable. It could be a specific action, or it could be a no-op action if the value is not changed by a given action, right? So that was the idea. So they introduced these additional, I call it an S variables, like the variable setting the value of that state variable, and then of course they connect this pair which says this action is setting this value. Then they need to connect all these action variables to the real action, which means that all of these will be no ops, but one action will be there. And of course, then they define the preconditions for this action only, right? So in the original model, it looks like this. So the precondition is defined for this action using the implication. And this is the effect action, which is defined between pair of these two variables, the action 1 and the state variable. And then the frame constraint is defined by setting the constraint that if this is a no-op, then I know that these two variables, these specific variables, must be equal. So the no-op is described between each row in this diagram. Okay, and then we need a set to describe the relation between all these variables and that action variable that is actually selected, which is called a channeling constraint, and it says something like this: if this action is affecting a given variable Vj, then the corresponding S variable must be assigned to that action. And if the action is not affecting that variable, then this state definition action should be no op, right? So if it's the action that is modifying the variable, it must be filled there. If it's not that action, it will be no op. So in this case, we will ensure that if this action is selected, exactly the right variables will be filled by this action, and all other variables will be filled by the no-op action. Okay, so that was the original model using the logical constraints, and we proposed the reformulation using table constraints again. So what we did is we model these constraints using tables. Rather than implication, we really put all pairs of compatible values in a table, right? And we also use the table constraint for the channeling constraint. And I think we kept the frame constraint in the logical form because there was not a lot of reason to describe it as a table. Okay. No, it was included, but it was included as a logical constraint, meaning we did not reformulate it into the table. It was there, it must be there, but not reformulate. Okay, so this is the second model, and let me now show at that time the best model, which was proposed by Lopez and Bacchus. It was called a CSP plan, and it was based on clever idea that it's somehow appearing already in the GP-CSP model before. And the idea is that rather than focusing on describing how action is changing the state from one to another one, we should focus on describing the reason why a given state variable is assigned to a given value. And by this refocusing, we can encode the effect constraints and the frame constraints together using a single constraint, which is called a state transition constraint. So the original model, they keep the description of precondition as before. If the action is selected, the precondition must be true, but they combine the effect and frame constraints into a successor state constraint, which basically says a value of a given state variable will be some specific value val if and only if there is an action which is setting this variable I to value val, or the variable I in the previous layer was equal to this variable val, and the selected action is not modifying the variable I, right? So we combine the effect and the frame axiom by describing why a given state variable has assigned to a given value. And that's enough, right? So we don't need any other constraint because everything is modeled here. This is just a description of what I said. So these are the actions that are modifying the variable I to value val, and these are the actions that are not touching that variable at all, right? So it corresponds to non-effect actions from the previous model. So again, we can model it in this way using implication and equivalence constraints. And again, we propose to reformulate it by using table constraint. So we use a single table constraint to describe the precondition, which is very similar to straightforward model. We just have a small number of columns because it's just one layer included there. And also, we use a table constraint to describe successor state constraint, and this is actually ternary constraint. We have a state variable before, action, and state variable after, right? So we just need 3 columns in that table, and we can describe this equivalence constraint using a table. I think I will show you an example because this is an important model, how the tables are really looking. So this is a precondition constraint for the actions. This is the model with 1 robot, 2 locations, 1 container. So you can see these are the 6 actions. I just put the names of the actions here. So the precondition of moving robot from location 1 to location 2 is that the rlock location is location 1, and I don't care where the container is, so this is like an empty cell, anything can be there. And this is for the loading, so we can see for the third action there are 2 preconditions. The robot and container must be both at location 1, and for another loading both must be at location 2. Regarding the successor constraints, for each state variable we have 1 successor state constraint. So for the location of the robot, this is how the table looks. So we say, okay, if the location of the robot should be location 1, there are 2 reasons for it. Either action 2 is used, which moves the robot to location 1, or, this is this line, actions are not modifying the location of the robot, which are actions 3, 4, 5, 6, loading and unloading, right? So before the location must be 1 to be 1 again in the next step, right? So first and third rows are describing this 1 equivalence constraint from the previous slide, and similarly the second and fourth row are describing the other equivalence constraint for it. Okay, so this is for the location of the robot, and similarly we can define the constraint for the variable position of container. Also again, there are, you can see the pairs of rows. So this is a description of changing the position of container to location 1, which is done by action 5, unloading. And this is a part of the constraints for preserving the position of the container, which is done by actions 1 and 2 that are moving the robot. Okay, and similarly for location 2 and for position at the robot. So these are all constraints that are defining our example problem. And let me now show the comparison of all these models. What's the effect of reformulating the models into these constraints? So first, the total number of constraints is now much, much smaller. but the constraints are larger. These are tables, and these are logical constraints. So we can see the n is the number of layers, and this is how many constraints we need in each layer. So you can see it's much smaller here. This is an explanation of the letters. So I will just skip it to show you the experiments. So this is a runtime. I don't know if you can see it, but basically, first, this is logarithmic scale, right? So logarithmic scale. These full dots are the original models with logical constraints, and the empty dots are the models after reformulation. So you can see just by reformulating the constraints, the idea is the same, but using the table constraints instead of logical constraints, we are usually order of magnitude faster. Order of magnitude faster for the same problem by reformulating the constraints. So the best model was the CSP-PLAN model reformulated, the last one that I showed you. So it was really the best model, and you can see it's 1, 2, 3, 4, 5 orders of magnitude times faster than the straightforward model not reformulated, which is a huge jump in runtime. And we can do even better. So we can now take this best model, and you can see that it's really best for every problem. We take the problems from IPC, so we did a comparison, and this was really best for every problem. And we say, can we do it even better by introducing some constraint satisfaction techniques into the model? And the answer was, well, let's try. We will see. Okay. So the first approach that we tried was the classical method known from planning as lifting. So the idea of lifting is that we should not decide the action right now if we do not have enough information which action should be there, right? So it could be too restrictive, because if we assign the action, we may find later that the preconditions of these actions are not satisfied. So what we can do is that we select the goal variable, but instead of assigning a value to action that is assigning this goal, we keep the domain of the action variable larger by using all actions that are setting this value of the goal, right? So we keep all the actions there rather than selecting just one of them. So instead of labeling the variables, we are using a search procedure which is called domain splitting. So we take a variable and we split the domain into two disjoint parts, and we explore them separately. Okay? So it was implemented using splitting of variables domains during search. So what was the effect of this? So this is the original CSP-PLAN reformulated, and this I don't know what's the purple color. It's after we add the lifting. So you can see it's usually better, but not always, because it may guide the search to a wrong branch that is explored first. But at the end, it's just a slightly slower. No big slowdown. So this was first improvement. The second improvement was based on idea that if we have two actions that are not interfering, if we swap the position of these actions in the plan, we obtain exactly the same plan. But in CSP, we need to explore both of these plans during search because they are good candidates, right? So the idea is that if we have non-interfering actions, we can say that they should be processed in a specific order. It's somehow similar to what's known as exist step semantics in parallel planning, right? So it's very similar. We say if we have these two actions in a sequence, explore just this order of these actions. Don't try to explore the other order because it will be the same. So we again model this property using table constraints that are saying which pairs of actions can follow each other in the plan. Okay, so that was the idea. So it's called in CSP it's called dominance rule, because we are adding constraints that are removing actually some solutions, right? But solutions which are dominated by other solutions which are kept there. It's also called symmetry breaking constraint. Okay. Exactly. Yeah, dominance means that you really prune some solutions from your search space, but you are sure that some other solutions are still there, which are dominating the solutions that are pruned. So it's a more general than symmetry breaking. Yes. Okay, so this is the effect. So again, the black one is the original model, and this is like a blue one is with the dominance constraint. So again, you can see that sometimes it's helping, sometimes it's make it slower. The explanation why makes the solver slower is that if we select the actions in a different, or I mean, if we force the actions in a different order, we may, in some sense, force the search procedure to explore different branches than if we use the previous order. So it may need to explore something, different part of the search tree that is not explored if we force a given order. That's the reason why it's a slowdown. Okay. Yeah. Question here and then. We use just the classical independence between the actions and just between, and we pose the constraint just between a pair, not between a sequence. So it was just for pair.
Not per state.
Not per state. Yeah, it was defined in advance. Sorry, I should say, yeah, all these graphs are for runtimes. So we measure runtime. I don't think, I think it will have more nodes because, as I said, we actually look at some of these examples and we notice that by forcing a given order of actions, then the search procedure is going to a different part of the search tree, and there are other set of nodes which would not be explored if we use the other order. So I think the number of nodes will be really larger here, because by adding this constraint we are not adding that much to the constraint propagation. It's not that time computationally expensive, right? So I think it's the number of nodes which is the reason for this increase. Okay, so that was the dominance constraint. I'm already late, but okay, let me try. So the last idea was really derived from constraint programming, and it was based on what's called a singleton consistency. Our consistency is a nice procedure, but it's not globally consistent. And there is an easy way how to make a consistency level stronger. It's called singleton consistency. The idea is that we assign the value to the variable, and then we make the problem arc consistent. If it's not arc consistent, you know this value is wrong, right? So you can remove it from the domain of the variable. And you do it for every value of every variable, and then in this case you can easily make arc consistency stronger. But you may guess it's computationally expensive. So we must be very careful which variables and which values you will be trying. Okay. So we try to apply this idea to planning, and it was motivated by observations that sometimes at the very end the domain contains actions that cannot be there because the preconditions can't be satisfied. This is what, for example, mutex constraints try to solve in graph plan problem, but we don't have mutex constraints there. So we use a very simple idea of assigning value to the action variable in the last layer and trying to find action supporting this action in the previous layer. Not a complete plan for it, just one step back, okay? And we did it just for newly added actions to the last layer, because if we are going in search, then the domains of action variables are actually increasing because you have more and more actions that are applicable there. So we just take the actions that may appear in the last layer and not in the previous layer, and for these actions we tried if we can find support for them by singleton consistency, meaning we assign this action to one variable and we tried an action in the previous variable which is giving precondition of that variable, okay? So that was the idea. As I said, it was implemented using the singleton consistency, and this is how it's working. You can see it's going up and down. And now the reason for up is really that it's computationally expensive. So this is not increasing the number of nodes. No, it will definitely decrease the number of nodes there. But running the test is very computationally expensive. So therefore, the runtime is sometimes much, much worse, right? But this is the nice part. for some problems that we are not able to solve with the previous model, with singleton consistency we help a lot because we remove actions that cannot be used, and the other models need to try them as possible alternatives. But still, I mean, it's not convincing. I mean, sometimes it's worse, sometimes it's bad. So what sometimes it's good. So what we did is we try to put all the models together. Okay, so we started with the first model, then we added lifting and dominance, which is the yellow one, and then we added also the singleton consistency, which is the red one. Okay, so this is a planner that we call a SEP, sequential planner, based on constraints. And you can see, okay, sometimes it's slower, but usually when the problems are becoming harder, then combining all these techniques pays off. Okay. So this is a planner called SEP. Okay, I'm already late. So now the question is, I can now describe you more advanced planning models based on parallel planning, or I can skip to the end of the tutorial. So it's up to you, because I'm already late. So it's up to you if we still have, well, before the coffee break. So perfect. Okay, so let's continue. I decided. I thought it's 9:30. So perfect. So we still have a lot of time. Okay. So we were not happy with these planners. Okay, we can improve the constraint models, but we are not competitive with state-of-the-art planners. I mean, this is not the red one is not competitive with state-of-the-art planners. It's still much slower. So we say what we can do better. So let's try to see the problem completely differently, not as a state transition diagram, but as a synchronization of state automata describing how each state variable is changing separately. So that's something similar to idea of timelines that is used in real life planning. So what do I mean? For each state variable, we describe the possible transitions of values of this state variable. We call it a finite state automaton. It's also known in planning as a domain transition diagram. There are some minor differences, but basically it's the same idea. So the idea is that we have nodes which are values of a given state variable, and the arcs are describing how the values of these state variables can be changed by actions, FCAS, right? So if we want to change the location of robot from location 1 to location 2, we need to use action move from location 1 to location 2, and vice versa, right? And if the action, if the domain, if the value of the state variable is not changing, we use arcs annotated by the no-op action. So it's very similar to description of these constraints from the GP-CSP model. We have the state variable and action describing how the action is changing this specific state variable, right? And of course, the initial state in the automaton is the initial value of the state variable, and the final states are the required values of that state variable. So if we require the container to be moved from location 2 to location 1, we have one initial state, one goal state. For the position of container, for the position of robot, we know that the robot is at location 1 at the beginning, and the robot can finish anywhere. So we have all states to be final states. So we define these separate finite state automata for each state variable, and then planning is finding a path in each automaton from the initial state to the goal state. But these passes must be synchronized, meaning if I do some action in one automaton, the same action should be done in the automaton for the other variable if it's changing this variable, or no-op should be used there. What I mean, okay? So yeah, so this is the description. So what I mean is that for each state variable, we will be looking for a path. This is a description how we are changing values of the state variable from location 1 to location 2 by this action. And we need this synchronization, which basically says, oh, if I'm doing loading at the C position, then the robot should not move. It must be at location 2. So at the at the automaton for the location of robot, I should be using no-op location 2 action. The robot is at location 2 and it will be a location 2. It's like a prevailing transition. I mean, it will stay at the same value, right? So these red arcs are describing these synchronizations between the constraints. There is no synchronization here because the move of the robot is not related to the position of the container, so the value of the container could be whatever we want. The only restriction here is that we cannot load the container, but this is ensured by the synchronization, because if we start loading the container, it must be synchronized with this action, which should be no-op, right? So if we select move here, then the only actions for this other variable will be the no-op actions. Perhaps I'm not familiar with that automaton, so might be. So it may be, yeah. Yeah. So I think so, because this is what we actually need there. So. Okay. So I think in conceptually, yes, the answer is yes. Okay, so this is the idea. So now we need to encode it. So we call the new planner PUP, parallel planner, because if you look back, we actually allow parallel actions, because if two actions are not interfering, then it's fine, because the synchronization constraint is not defined between them. So we allow parallel actions of non-interfering if they are non-interfering at the same step, which is a big advantage, because then we don't need to remove these symmetries. And you saw that the dominance rule modeling the symmetries was working, but it was not exactly what we wanted to be there. So in this case, we don't need to remove any symmetries, because all non-interfering actions can be in a single step. Okay, so it's a called time-right model. We have state variables like before, but now instead of having one action variable, we have for n state variables, we have n action variables, which will be defining how each state variable is changed by a given action. Okay, so otherwise the model is similar like before. It's a layered graph, and this is a constraint defining how this action is changing the state variable from one value to another value. So this is basically a constraint describing the finite state automaton for z state variable, right? So it's a ternary constraint describing this. Then we need to describe the synchronization constraints. We use a quite complex model which basically says for each action that can be used there, put a constraint between this variable and all other variables that may contain any of these actions to describe the synchronization, right? So we say, for example, if this action is changing value of this state variable and of that state variable, then this constraint ensures that if the action is used there, it must be used there as well, because the action is changing more things in parallel, right? So this was the most complicated part of the model, how to formulate these constraints automatically from the PDDL description. But at the end, that's it. So we just use these two type of constraints, and we then realize that we can make the model stronger. Sometimes you have a core model, and you can add redundant constraints that are not necessary to define the solution, but that helps propagation. And we say, okay, what we can do here, we can add constraints between pairs of the action variables for a given state variable that are saying that these two actions are compatible. It's actually very simple. Actions are compatible for a given state variable if one action is setting the value and the other action is using this value as a precondition. So if they are incompatible there, they cannot be in a sequence, right? You may say that this is visible here. Well, it's not exactly. The ternary constraint does not put exactly these two actions in relations. There is it does not putting these two actions in relations. It's putting the action and the state, right? So we don't have the direct relation between these two actions. They are just interfering through the value of the state variable. If the state variable is not yet known, we may still select an action which is incompatible with this one until we instantiate the variables. We don't know it, right? So that's the reason why we put this constraint between the actions to make the model stronger. So this is a PUP model. How is it working? Yeah, the search strategy. For this model, we use more or less a standard labeling procedure. We just instantiate the action variables, not the state variables like before. They are instantiated by the inference. And for the variable selection, we use classical DOM heuristic, meaning variables with the smallest domain are selected first. But we included only variables that in the domain, in the current domain, have some real action. There might be the real action and no-op actions, right? So if I have a variable which contains just the no-op actions, I don't need to assign this one because it will be, it's just the value of the state variable will be the same. We just don't know which value of the state variable we need, right? So we don't need to decide these actions. They will be decided by propagation through the constraint. So only variables containing real actions are assumed. And question? Okay. And for selecting the value, we again use the domain splitting principle rather than assigning a specific value. And it's working like this. The domain of the action variable contains some no-op actions and some real actions. Usually we prefer in the plan to have a small number of actions. So what we did is that as the first branch, we reduce the domain to just no-op actions, and all of them were zeros, right? So it was not always assignment. And for the real actions, we explored them as the alternative, but using the labeling. So we assigned the real actions one by one, right? So it was like a mix of domain splitting and labeling enumeration of this variable, and it was working quite well. Okay. Yeah, and of course, only action which contains whose domain contain real actions will be enumerated. So how does it compare? So this is the best model from the sequential planning, our SEP planner. And again, we took the domains from IPC competition. This is the number of planning problems in each domain, and this is the number of solved problems from these domains. And the red is the best, meaning the largest number of problems that we can solve. So we can see that now the parallel planner is quite good. It's usually better than the sequential planner, but not always. I mean, for OpenStax, we are still quite bad. For elevators, it was slightly worse, but not that big thing. So it looks like there is some small improvement. So let me now show what's the big improvement. This is the comparison of runtimes, the sequential planner and the parallel planner. I should say that this number of solved problems is that for each problem we use a 30-minute limit, right? So in 30 minutes, if we solve the problem, we have the solution. If not, we have no solution. So this is a comparison of runtimes for some Zeno Trevor domain, and you can see the big difference, right? So we can still solve these problems, but look at the runtimes. In the parallel planner, it's 3 orders of magnitude faster for this specific domain. And this is a comparison of size of the plans, because of course you can say this is not a fair comparison, because we are comparing sequential planning and parallel planning, which has the advantage because the sequential planning is looking for shortest plans, while in parallel planning we are looking for make-span shortest plans, which may contain actually more actions. Okay, so this is a comparison of the number of actions, and you can see that even in our parallel planning, it's actually not that bad regarding the size of the plan. This is a number of parallel steps, number of layers that we need to find a solution, and this is the number of actions that we extract from the parallel steps. So there are some parallel actions in each of these steps. And you can see that they are not that bad from the optimality. I mean, this is the shortest plan, 8 actions, we have 11, right? So this 11, we have 14. 11, we have 12, right? These are the lower bounds, so we know the planner did not finish, but we know that at least this number of actions is necessary. And you can see that, again, we are quite close. I mean, the lower bound is 12, we are 16. Lower bound is 10, well, it's 50% more. But I mean, it's not like thousands actions more in this parallel plan. It's just a few actions more. Yes?
In this sequentialization of the actions, are there any redundant actions?
We did not check redundancy there. I don't think there should be, because there is no reason to introduce redundant actions in this model. But it might be that some sequence can be removed, because the parallelization is very simple. We take the parallel step and any order is fine, right? Any order. So we use the for each semantic for the parallel step.
That the solver introduces or selects some actions that not really
It may be, yeah, but that's why we that's why we use the search strategy where we prefer the no ops first. So in this way, we are trying to prevent the situation that we are selecting actions that are actually not necessary, right? But it's not guaranteed, right? But it's just the idea of the search procedure.
So I mean, this could even be better, the approximation to the optimum. I mean,
Yeah. Other question? No. Okay. So this was a parallel planner. So this was the model of the parallel planner. We have the sequencing constraints, state variable, action, next state variable. We have synchronization constraints, and we have redundant action sequencing constraints.
I do have one question.
Yes.
The runtime was a bit longer, but taking these automata and then having to do the sequencing, you end up with
It's no, the number of actions is the same. Well, there are these no ops, but it's not that bad. I mean, no, it's not. I mean, we did not observe any problem in this, and these runtimes they include the translation to the model, definition of the constraint as well, right? So it includes the definition of all the tables. It's included in the runtime. Yeah. Okay, this one.
Okay, so SEP, is that always finding optimal solution?
Yes, that's because of the principle of extending the layers, right? And
You're really not comparing apples with apples.
yes, exactly.
Whenever you go to from optimal to non-optimal.
Yes, exactly. That's why I said that it's not really fair comparison, because SEP is plan length optimal planner, and PUP is make span optimal planner. So they are looking for different solutions. That's the reason why I put these columns here to compare how close we are to the optimum. But yes, it's not completely fair. Okay. And then any other questions about it? Yeah. So for us, it was important to produce more plans than shortest plans, because that's what we usually need. We need some plan rather than the shortest plan. Okay.
But it also probably explains why it's faster in a way too, because it's not checking, it's not guaranteeing optimal, it's not checking every possible.
That's one way, but I think the major reason for the increase of numbers of solved problems is removing the symmetries, because in SEP we try to remove symmetries, but just between the neighboring actions. But in PUP, we can put a set of all actions in a one layer, and in this way we may remove much more symmetries, because if I have 5 actions in a single layer, then actually 5 factorial of symmetries is represented as a single plan in PUP, but we still need 5 factorial plans to be explored in SEP. So I think the reason for the much better runtime behavior is because of this. Not because of we are not looking for the shortest plan, but because of removing these symmetries. It's like the graph plan step in planning. It was because we removed many of these symmetries. So I think that's the major reasons. Okay, other questions? I might be at the end at the time. That's perfect. Okay, so this is the PUP model. 3 types of constraints, as I described: the sequencing, state, action, state, synchronization between actions in a single state, and redundant constraint between 2 neighboring actions. We look at it and we say, how this action sequencing is defined? Well, if this action is compatible with a given value here, and this action is compatible with this value here, then these 2 actions are put as a compatible actions, right? Because the effect of one action is exactly precondition or not, it's precondition for the other action. So we say, do we need the sequencing constraint at all? And the answer is no. Because we don't need to know the state. We just need to know that if this action is there and the other action is fitting through a given value, then this is exactly what we need to know, right? So we can remove the sequencing constraint from the model, but if you remove sequencing constraint, you don't need the state variables at all, right? Because there is no constraints touching the state variables. So we have a model which is just defined using the actions. Of course, you need to select the actions that are compatible with the initial state. That's the restriction. And you need to select the actions which are relevant for the goal state, right? So to represent the initial state and the goal state. But at the end, you don't need to know the states in between, right? And we call this model PAP2, Parallel Planner 2. What's the effect? That's it, right? So you can see just by removing variables and constraints from the model, we increase the number of solved problems. So now we are best everywhere with one domain where we still can't solve it. We don't understand the reasons so far. But for all other domains, we can find the plans much faster, right? So constraint modeling does not always means you are adding more and more redundant constraints to propagate more. Sometimes the opposite way is better, right? So you should remove some constraints that are not contributing to solving the problem, and even some variables in this case, okay? And this is the comparison of runtimes for the same Zeno travel problem. So okay, for smaller problems, it's slightly slower, but we can see as the problems are increasing, we still keep a good runtime efficiency. Regarding the plans, we found exactly the same plans, right? So it's not different. The PAP and PAP2 at the end they are producing the same solutions. So it's a fair comparison between PAP and PAP2. And with SAP, I explained it before. Okay.
So I think that's so you're removing these state constraints because what, you don't need them? Or?
Yeah, exactly, right. So we realize that actually this redundant constraint is defined in such a way that it models the sequencing constraint, because the idea was I have an action, it's setting the value of some state variable, and the other action is using this variable as a precondition.
But like the successor state axiom, you can do away with the frame constraint by creating these ternary tables or whatever. You can do away with the sequencing constraints by incorporating them into the action.
Yeah. That was the idea. Yeah. It's but you need to do it for each state variable, right? So that's why it's not possible to do it before with just one action variable and one action variable. We do it for each state variable.
You use them and then you get rid of them.
Yeah. So it's like a
Easily sort of creating them somehow.
yeah.
Lazily, pre-compute them.
Yeah. So really it was removing the constraints, and we obtained the planner which was the best constraint-based planner for some time, and there are now slightly better planners. Okay, so let me go to conclusions. So what you should take away? First, if you want to use constraints to solve any problem, what's critical is constraint modeling. This is what's defined if you can solve the problem at all and what will be the efficiency. We use the Sixtus Prolog for all these planners, and if you use other constraint solver, there will not be big difference because all constraint solvers are based on same ideas, more or less. There might be slightly faster, some of them, but what's the critical is the modeling part, right? So how to encode the problem as CSP. And I think this is also critical for planning. So now everyone is using PDDL. So we are stuck with PDDL. I don't think this is the good modeling for real-life problems, right? So it's about the modeling. If we can use a different model, we can produce perhaps much better planners, like in this case. So modeling, in my opinion, modeling is critical, and solving algorithms are important, but the model is the most critical because the solving algorithm depends on the model. That's my view of it, right? Usually in CP, models which are pruning more inconsistent values are better. Of course, there is a trade-off that if you prune more values, you may need more time to do it, right? So you may need stronger consistency techniques. So you need to find a trade-off between how many values you prune by the constraints and how many remaining options you leave for the search procedure there, because search is still there. The propagation is not complete. Okay, and as I said, search is still important because search is a very nice way how you can encode your preferences about how to solve the problem. And I gave you some examples how we encode specific search procedures for solving planning problems. We say, oh, you should select this type of actions there because we believe they are contributing to finding the plan, right? So if you know somehow if you have some heuristics which actions are promising, these are the actions that should be tried first in the search procedure, and then you will try the other actions in backtracking to ensure completeness of the algorithm. Okay, so now the question is this really the best model? No more. This year at AAAI, some guys introduced a different model, transition constraints for problem planning, and I can tell you what they did. So I showed you the PUP2. So what we did in PUP2 was that we removed state variables and kept just the actions. What these guys did, they removed the actions and kept just the state variables. And they use the Minion solver, and they have an even faster solver comparable, I think, with FF in efficiency now. So they also removed some variables and some constraints from our model in a different way, and they actually achieved even better results than we have, right? So this paper this year at spring. Okay, so I was talking about how we can solve planning problems completely using CSP. But of course, we can use constraint satisfaction techniques in planning in general, for example, for solving specific subproblems. So you can use a planning algorithm, and inside this planning algorithm, you can use a constraint-based techniques for solving like temporal and resource reasoning within the planning, because this is where CP is very good, in temporal and resource reasoning. There are strong constraints, strong consistency techniques that can be incorporated into other algorithms. So we don't need to model a problem completely as a CSP. We can just exploit part of the CSP for solving parts of the problem. This is a list of some references. So two books that I can surely recommend for CP, handbook by Rina Dechter. She will be giving another tutorial tomorrow. Sorry, not the handbook, textbook, Constraint Processing, and the handbook, which is a really big book for constraint processing, edited by Francesca Rossi, Peter van Beek, and Toby Walsh. Also very good book, some information about CP. Regarding the models that we started with, these are the papers describing these models, including the textbook by Malik, Dana, and Paolo, and these are I didn't mention the C-plan. C-plan was perhaps the first planner designed to exploit constraint satisfaction, but this planner was not designed automatically. It was designed manually. So for a given planning problem, they manually encoded the problem as a CSP and then they solved it, right? But all these other planners are doing automated translation. So they use as an input PDDL and then translate the PDDL domain models into CSPs. And the same is for our planners. So we start with the PDDL, we translate it into multi-valued state variables using Maltese translator, and then we encode the constraint models automatically from these problems. And yeah, this is the paper showing the best constraint solver so far that I mentioned from AAAI this year. Okay, so that's it. Thank you for your attention, and if there are any questions, I can try to answer.